Right, so I'll talk about RefinedRust, which is a tool for high assurance verification of Rust programs. This is originally based on a PLDI 2024 paper with Michael Samler, Ralf Jung, Robert Krebers, and Derek Dreyer. And since then, we've been developing it further with help from Vincent, who is also here today. Currently, I'm also working on with people from IBM Research on applying it to a case study that I'll talk about later today. And in the process, we are adding new features to RefinedRust. If you have any questions during the talk, I'm happy to take questions whenever it is convenient. Okay. Yeah, so everyone of us, I guess, is excited about Rust because it gives us systems programming with zero-cost abstractions for memory management. And that is why it's enjoying growing popularity. For instance, now Rust is just the second language after C to be used in the Linux kernel. And one of the reasons for that is also that it brings modern programming paradigms familiar from higher-level languages to systems programming. And another big reason is that it aims to provide memory safety. For instance, no null dereferences, no use after free, no data erases, and so on, which are big problems for code written in C. And with just that, just using Rust already basically rules out a huge class of common vulnerabilities encountered in system software in a way that is accessible for most programmers. And there's one catch here, which is unsafe code. So let's look into that. Unsafe Rust is kind of a double-edged sword. And while most of the time safe Rust is more than sufficient for everything you want to do, unsafe Rust is really crucial to the success of Rust, I think. A lot of code that you can safely use in Rust without fear of memory unsafety internally uses unsafe code to provide that safe API. For instance, that is the case for Rust's vector library. And in this excerpt from vec here, you can see how unchecked pointer arithmetic is used to add a new element to the vector. On the other hand, the problem with unsafe Rust is that it leaves Rust's nice safe ownership patterns and often is not really well behaved. So from the perspective of a verification tool engineer, you need an accurate memory model to capture the intricacies of Rust's pointer semantics, and you need to explicitly reason about ownership, which makes things much more complicated. And this is one of the, and so we try to tackle that problem. And the way we do that is by basically trying to turn RustBelt into a verification tool. So we start out with ideas from RustBelt, which is a well-known semantic model for Rust. And RustBelt really shows us how to soundly handle Rust's reference types, which are pretty tricky to get right. And it allows us to manually reason about unsafe code. But then we need to figure out how to turn that into a practical verification tool. Using RustBelt is a lot of manual work, and it can't really reason about functional correctness. So for that, we take inspiration from work on RefinedC, which is an ownership-based refinement type system for C. RefinedC, at a high level, combines Rust-inspired ownership types with refinement types for functional correctness reasoning. And since unsafe reasoning is already quite common in C, after all, everything is unsafe, it naturally handles unsafe style code with its type system. And on top of that, RefinedC's type checking is automated to a fairly high degree using its lithium separation logic engine. Okay, this is the high-level approach. It's not as straightforward as just plugging the two together, and I'll get a bit into that in my talk. But for now, let's look at what RefinedRust is. RefinedRust's goal, as for many other Rust verification tools, is basically to verify memory safety, but in our case, also of unsafe code, and functional correctness, as well as panic freedom. At the base for that, we have a formal model of Rust or an approximation of that in the form of an operational semantics that we call radium. And this is formalized in the Rocq prover. And then we have an automatic translation, which is implemented as a Rust C driver that takes the borrow checked mer and translates that mer code into our radium representation in Rocq. And then we have in Rocq a refinement type system that is designed to prove memory safety and functional correctness. of the Radium code, and it has a semantic soundness proof that is based on the RustBelt soundness proof. And finally, we have proof automation based on the lithium separation logic engine from RefinedC to guide the application of RefinedRust's typing rules. Okay, that is the high-level picture. I want to get a bit into a few design choices we make with RefinedRust and what motivates them. Our first design goal is basically to strictly extend safe Rust. The idea here is that safe Rust verification should always work predictably. Unsafe Rust, on the other hand, is trickier and that may turn out more unpredictably. And this serves to have clear user expectations, at least about safe Rust. And for safe Rust, we can furthermore reuse Rust's memory safety proof. I'll get to that in a bit. Secondly, we want RefinedRust to be reasonably uninvasive. So we want to leave the code that we verify untouched and have clearly distinguishable annotations that guide RefinedRust, in particular for the specifications. That serves to keep up the readability of the code that we are verifying, and that software engineers don't have to learn a new verification language just because we want to verify the code that they are writing. Furthermore, we want RefinedRust to be foundational. So we gain high assurances by generating proofs in the Rocq prover. And this serves to give us high trust and a much lower risk of oversights or soundness holes than in non-foundational verification, for instance, based on model checking or SMT solvers. And that, I think, is especially useful and well motivated around tricky, unsafe shenanigans. And finally, we want it to be selectively automated. We strive to automate what we can automate. And if we can't automate something predictably, we resort to interactively asking the user to help with what we can't automate. Just by eyeballing, I would say, like in the popular assurances versus automation diagram, I would just put RefinedRust somewhere here. We get pretty high assurances because we are foundational. We are not at the top of the line when it comes to automation or speed. Okay, how do we achieve these design goals? I'll briefly give you some idea of the high-level design choices that we make, and then I'll get into some more detail later. For strictly extending safe Rust, we design a refinement type system that extends Rust's type system. Extension here in the sense that basically for every Rust type that you see in surface level Rust, there's a corresponding RefinedRust type and but a refinement version of that. And we have type safety contracts for these RefinedRust types that are based on the RustBelt safety model. And then we replay Rust safety proof by utilizing borrow checker hints to guide the type system for safe Rust. On the uninvasiveness part, we add specifications to the Rust source as attributes. But manual proofs and hints, we resort to adding to Rocq proof files instead of keep putting them into the source code, into the Rust source in order to keep the Rust source clean. For the foundational proofs, we strive to have a very mechanical, very straightforward translation of the MER code that we translate into our model in Rocq. In order to keep that simple and easy to understand that we do nothing funky there. And we prove the soundness of all our typing rules, all our reasoning principles in Rocq, and check all the generated proofs in Rocq. Finally, for the selective automation, except for bugs that occasionally do happen, the ownership reasoning and the safe type system should be fully automated. Unsafe Rust will need hints occasionally, and side conditions about user specifications have lightweight automation for functional reasoning. Okay, So this is hopefully some of this sounds reasonable to you and sounds like sounds nice to have. I think foundational proofs are cool, but our design choices also have drawbacks that I want to be clear about. As I already said, in the automation versus foundational diagram, RefinedRust is relatively slow. For one, because we don't try to optimize the MER code that we are verifying, and it usually blows up quite a lot. And secondly, because we do foundational proofs in Rocq, which tends to not be very fast. Secondly, we have relatively little automation of pure facts, also due to the foundational proofs, because foundational solvers in Rocq are far less intelligent than, for instance, SMT solvers. And finally, we tend to have less or slower feature support because when we add new Rust language features, this always means significant effort because we have to maintain our soundness proof in Rocq. Okay, that's the high-level overview. If you have any questions at this point, I'm happy to take them. Otherwise, I'll continue. So for the rest of the talk, I'll talk a bit about how, from a user perspective, RefinedRust works. I'll then give you a bit of a high-level view of some interesting things that I think are interesting in the RefinedRust type system that might be of interest to other people working on verification tools. And finally, I'll talk a bit about our ongoing case study with IBM Research. Okay, so how does RefinedRust work? I'll start with super simple safe Rust code, super trivial safe Rust code, namely this function add 42 that takes a 32-bit signed integer x and returns x plus 42. If you want to verify it with RefinedRust, you add a returns annotation x plus 42, and basically every Rust variable, in this case x, has a corresponding mathematical version living in RefinedRust's mathematical refinement model that you can refer to here, and you can say, okay, the return value should be x plus 42. If you have used other Rust verifiers, you might wonder what happens with the potential overflow here. And so indeed, we need a precondition that makes sure that we don't run into the overflow case, because we prove that the code is panic-free. So we have a precondition that says that x plus 42 must be representable in 32-bit signed integer. And the specification works because the specification level x is an unbounded integer, so we can safely do the x plus 42 addition here. Okay, then we have the code and the specification. Now let's use RefinedRust. First of all, when you call the RefinedRust frontend, we will call into the Rust compiler and get the borrow checked MER code and generate from that the representation of the radium code in Rocq. And we also interface with the Polonius borrow checker during this process. I'll get a bit into that later, in order to generate hints for the RefinedRust type checker. And next to the translated code, we also generate a representation of RefinedRust specifications as in the form of RefinedRust type assignments and lemmas in Rocq. And then these lemmas will be proved by the RefinedRust proof automation. And this process then can either fail or it can succeed. If it succeeds, you're happy, hopefully. If it fails, your specification might be wrong, your implementation might actually be wrong, and we've discovered a bug. Or the proof automation might not be smart enough. And in that case, you can interact with Rocq and the RefinedRust type system in order to supply manual tactics and hints to make the proof succeed. That's the high-level process. Okay, let's look at a small example, namely a part of Rust's vector library. That is, I think, a good example because it's inherently implemented with unsafe code and so makes some interesting use. So this here is a variant of vec for dynamically growable arrays. That is a bit simplified for presentation purposes, but it basically has a raw pointer to the buffer, storing the elements of the vector, a length field that contains the number of currently stored elements, and a capacity field storing how much memory is currently allocated in the buff field. And so to understand how to verify this, we first have to look at kind of what memory representation the vector library internally maintains. And basically we have the buff field points to a buffer that consists of an initialized segment in blue on the left, which contains the elements of the vector, and an uninitialized segment on the right with over-allocated memory. And if you want to verify this with RefinedRust, the first task basically is to make this representation invariant formal. And in our case, for that, we would just like to hide all this nasty pointer business. So we want to hide the buffer and the capacity and so on. And so we abstract the whole vector to the mathematical list of elements that is contained in the initialized part. Let's call that XS in the following. And then we'd like to abstract away all the details on memory allocation that is irrelevant for that representation. So let's define this formally. We do that in multiple steps, and you don't have to look at this too closely. This is just to give you an idea of how it works. Basically, first we have to come up with a mathematical representation and then relate it to the physical representation in Rust. That is this part. Then we define some invariants to represent the initialized and the uninitialized parts. And finally, we need some nasty side conditions to keep everything in sync, for instance, to constrain the size of the allocation. Don't look at this too closely, as I said. But the most interesting part is that we have to manually specify a type for the buffer using RefinedRust's array type here. And that crucially also requires exclusive ownership over the buffer as pointed to in the buff field, which really is the most important part of this invariant. Okay, let's get into some of the key functionalities of a vector, namely getting a mutable reference to one of the elements. And so this function here basically takes a mutable reference to a vector and an index I, and it should return a mutable reference to the element at that index, assuming it is in range. And we have to mark this as unsafe because this function does not perform any bounds checking on the index. And so for it to be memory safe, the caller has to ensure that the index I is in range. And this is precisely something that we can specify quite nicely in RefinedRust. And so we put some annotations. First, we want to specify that we return a new mutable reference to the right element of the vector. And for that, we use this ensures clause here, saying that the red value that refers to the return value has a points to the ith element of the whole vector. Here we use this .current syntax, which refers to the current value of the mutable reference. Right. And then, as I said before, we have to ensure that, or we have to require that the index that we pass to this function is in range. So that is something that we need to put in the precondition. Now, this looks like a reasonable specification, hopefully, but there's some part here still missing, which is what happens if we modify the element of the vector via the returned reference? What happens if we modify the ith element via this reference? And how does this get reflected in the whole vector? And for that, we use so-called borrow names, which are inspired by Rust horns and Crusoe's prophecy variables, which we use to communicate the final value of mutable references. So we have this self.ghost field, and this is the borrow name for the for this reference. We have one of these fields for each of the two mutable references involved here. And then we have this resolves clause, which says that the final value of the mutable reference self should be the current value of it, but with I replaced by a reference to the borrow name of the new mutable reference that we return to the function. So in the end, this just says, okay, the ith value gets updated to whatever we do to the mutable reference that gets returned. Right. I won't tell you too much about how we verify this in detail here, but I'll just mention that it's not super trivial because we have to reason about how handing out a mutable reference to the element respects the representation invariant that we specified on the previous slide. Because we kind of temporarily pass the ownership into the returned mutable reference. Okay. Any questions so far? Okay. Then let me get into a little bit of detail on RefinedRust's type system and how some of it works. As I said already, at a high level, RefinedRust's type system basically extends Rust's type system in the sense that if you have a Rust type inside Rust, then that you should have a corresponding type in RefinedRust. So there are mutable references, shared references, and so on. But you have, in addition, that every type has a refinement, so a mathematical value describing its current logical value, which is, for instance, as we saw before, mathematical integers for integer types, or the list of elements for the vector type that we defined. And then on top of that, we have special types for unsafe code that RefinedRust uses in order to reason about unsafe code. So specifications for Rust functions, then basically, if you don't provide any specification, you get as the specification basically the implied safety contract that if you pass in an element of or if you pass in the arguments and they are correctly typed at the argument type, then you get something out that then you get that the return value satisfies the implied safety contract of the type. And then if you put functional annotations on that function, you're basically augmenting that implied safety contract. Yeah. If you want, you can also override the default safety contract, of course. And then RefinedRust's type checker is implemented using flow-sensitive symbolic execution, essentially, in the lithium separation logic engine of RefinedC that I mentioned earlier. So let me get into one interesting aspect of this type system, which is how to capture intermediate states. And you'll see what I mean by that in a moment. And for that, let us look at this again slightly contrived function, which initializes a tuple of integers. Then we take a mutable borrow of the first component of the tuple. We use that a bit, and then we check that we correctly updated the value of the first component of the tuple. In Rust, if you do this, then the first component of the tuple will be inaccessible for the lifetime of the reference XR, as it is borrowed, of course. But then the question is, what is the type assignment of X after this? In Rust, you kind of have have the top level types, but these top level types don't really on their own allow you to express what the state of X is when we borrow one of its components. That in Rust is really like implicitly a part of the borrow checker state. But in the RefinedRust type system, we need to kind of make this, we need to make this state explicit, and we need to track that the first component is borrowed. And for that, we use so-called place types that allow us to express the intermediate states of the Rust type system and basically allow us to ascribe types to individual places that may be different or that may have more types to capture this intermediate state than you would have just when looking at surface level Rust types. And let me show you how this works. And I'm going to show you the intermediate type system states here that RefinedRust has when tracking this example. Of course, simplified quite a bit. In particular, I'll be omitting refinements, so like the mathematical values of integers, for instance. Okay, after the first step, where we initialize the tuple, we have the following state. We have for X the type assignment place, and then the surface level Rust tuple type, which basically denotes that X is a stack variable that contains a tuple of integers. This little triangle here is the notation we use for type assignment. Okay, then in the next step, we borrow from the first component. So we kind of, the RefinedRust type system kind of unfolds this into the subplaces. And then we do the borrow. We get a type assignment for XR, which is a stack variable, which contains the mutable reference to the integer. And for X, that is the crucial part now, we need a new type assignment. And concretely, we get a type assignment where the first component uses the so-called block type we have that says that this component is inaccessible for lifetime A. And the second component stays a place of a 32-bit integer and so remains accessible. Okay. Then we write to the XR reference. Nothing really changes here. And then afterwards, A implicitly ends the lifetime A. And so we can remove the blocked and get the full place back again. So the first component of X becomes accessible again, and we can fold it back if we want to. Okay, that is basically how RefinedRust tracks the intermediate states. There are a few more place types. That, for instance, one, if you do a shared borrow from a place, that behaves a bit differently from the mutable borrow version. But this is basically, this gives you basically the idea. Okay, so RefinedRust, having these place types defines a semantic model for Rust types, including these place types. And for that, we use an extension of RustBelt's lifetime logic with so-called pinned borrows that we use to model places below mutable references. And the way we can do modifications to these places. And the nice thing is that this place model validates some Rust code that's valid under NLL or Polonius that RustBelt does not validate because we can handle places more accurately than RustBelt does. And as a nice side effect, place types also help us to describe the intermediate states in the case of unsafe code that the Rust type system does not track. For instance, we can track the intermediate state when we borrow from below the raw pointer in the getUnchecked function. And we can also just use it to describe unfolded invariants on data types, like the unfolded representation invariant on the vector type that we defined earlier. And so place types are really crucial to how RefinedRust is reasoning, and we have different place types for these different use cases. Okay, that is, I hope, one interesting part of RefinedRust's type system. Let me briefly also get into how RefinedRust reconstructs Rust safety proof using Polonius. So as I said earlier, RefinedRust reuses Rust's memory safety proof for safe Rust. There's an informal theorem that should kind of hold for this, and is that if the Rust type checker succeeds, the RefinedRust type checker should also succeed when verifying pure memory safety. This is an informal theorem. I haven't proved it, and I don't think we will prove it. And also doesn't account for the fact that there may be bugs in RefinedRust, which make it spuriously fail. But this is kind of like, in spirit, what we are going for. But importantly, RefinedRust reproves the safety of all code against its Radium operational model. We don't trust the Rust compiler for its safety proof, and we have to prove that that the code is correct against our operational model. And for that, we need some guidance for handling lifetimes and borrow checking, basically. If you are a bit familiar with RustBelt, you will probably remember that there are these start lifetime, end lifetime annotations, and RefinedRust also uses similar annotations to guide the type system, which are generated by the front end. But there are a few more annotations because of how the translation works and because we do some things differently than RustBelt. And importantly, these annotations are untrusted. We don't have to trust the borrow checker. And if they are wrong, the worst thing that can happen is that the proof will fail inside Rocq. Okay. And for this, for generating these hints, we use Polonius, which is an alternative borrow checker implemented in Datalog. It's about a number of other Rust verification tools use Polonius, so this isn't really new. For instance, Prusty takes a similar approach to getting borrow checker hints when reconstructing the Rust safety proof. But for RefinedRust in particular, because we try to very closely follow the Rust type system, this is still interesting. And well, Polonius, in case you're familiar with it, it basically phrases the borrow checker in a nicely semantic way using so-called loans and regions. Loans are created for every borrow in the program, and regions, which are basically sets of loans, describe the lifetimes of, or describe all the lifetimes in all places occurring in variables in the program. And since this is so semantic, this is a pretty good fit for RefinedRust semantic safety proof. And so we kind of try to replay Polonius's safety proof. In our setting, every loan kind of corresponds to a RustBelt atomic lifetime, if you're familiar with that. And every region in every flow-dependent execution maps to one RustBelt lifetime. And then in our translation, we kind of keep this mapping, or try to keep this mapping in sync with the Polonius facts holding at every program point. That's it for safe Rust. For unsafe Rust, of course, there are some additional complications. Polonius doesn't really understand, for instance, when we borrow in this unsafe block from below the raw pointer. Polonius doesn't understand how this borrow from a raw pointer should be constrained. To prove this code safe, we should constrain the region or the lifetime of the returned value by the lifetime of the vector. Of course, we cannot hand out a reference that outlives the vector from which we are borrowing, but we don't really get that from Polonius. And so in these cases, because we don't really have a good heuristic that reliably could give us this, RefinedRust opts to ask the user to manually provide a constraint for this loan. So for instance, in this case, the user would supply the constraint that the lifetime of the mutable reference we are creating needs to be included in the lifetime of the vector, which should make sense, hopefully. Right. Okay, that's what I wanted to say about the RefinedRust type system. And does anyone have any questions up to this point?
I, for example, have some, but I think we can ask them at the end. Does anyone have immediate questions?
Okay,
Apparently.
then I'll continue. Right. So that's it mostly for RefinedRust. Now we'll have a slight context switch that hopefully will work. To talk about work that I'm working on with some folks from IBM Research who have the so-called ACE security monitor, and we want to verify core parts of that. So let me explain a bit of what the security monitor is and what it does. So if you look at traditional computing systems, for instance, let's imagine we have like some cloud provider and it offers you a virtual server. Then the cloud provider will have some hardware that runs a hypervisor, and this hypervisor runs some virtual machines. And these virtual machines, ideally, let's say you have some secret data that you're processing in the cloud. That secret data you don't want to leak to your competitors. You don't want to leak it to the cloud provider, and you don't want to leak it to other people running virtual machines on this physical machine. So you kind of want to isolate your computation. In a traditional setting, you would have to trust the hypervisor, the firmware, the drivers, and the hardware. And in particular, in the case of the hypervisor, you have to have a lot of trust because, for instance, Linux KVM consists of more than 10 million lines of code written in C, which is notoriously unsafe. So probably something somewhere will go wrong at some point. So that's not great. That's why there's confidential computing, which tries to provide an infrastructure to run computations confidentially. I'm presenting here one particular setting of confidential computing, one particular instantiation that we are in here. There are other settings that in which you could phrase this, but this is what we are looking at. And in this setting, you basically have confidential virtual machines, which contain confidential data or confidential computations, and you want to make sure that that confidentiality and integrity of that data and that computation is maintained. And in order to do that, there's this security monitor here, which you can kind of imagine as a firewall that sits between the hypervisor and the confidential virtual machine. The hypervisor can, as in the traditional setting, run other virtual machines which do not need to be isolated, but the security monitor tries to isolate the confidential virtual machine. And well, the goal here is that you don't have to trust the hypervisor and the operating system anymore. So that moves out of the trusted computing base. Of course, you have to trust the security monitor now, but the idea here is that you want to you can implement the security monitor with much less code, and so the computing base is much smaller. Okay, in the case of the security monitor that we're looking at concretely, this is kind of the architecture. that is architecture dependent. Basically, the security monitor runs at the highest machine security level, privilege level, and sets up the system at boot time, and then launches the hypervisor in a lower privilege level, and which can then take over the rest of the system. You can implement this generically with some hardware primitives, which I'm not going to go into in detail. But the goal then is to basically build an open source, formally verified confidential computing technology based on this architecture. Yeah, that's the big goal. As of course, still, even though the security monitor is much smaller, of course, it's still like a pretty sizable goal. But the people from IBM Research have implemented this. You can find it here under this link. And they've implemented it for RISC-V because that is an open architecture. And this architecture is becoming part of the RISC-V code spec for confidential computing. And since we are here at the Rust verification meeting, of course, this is implemented in Rust because of Rust's memory safety guarantees, which are pretty good in this setting. Okay, but the goal, of course, is to prove a bit more of than just memory safety. In particular, also because the security monitor contains unsafe code. So there are a bunch of properties that we would like to prove. At the top are security guarantees, for instance, that the VM data of the confidential VMs is actually confidential. This kind of is shaped like a pyramid because the top level security guarantees, of course, rely on lower level properties. At the very bottom, there, of course, you need to rely on the hardware being correct and not leaking all your data. Above that, we have language memory safety, which in the case of Rust is already there for large parts of the code, except for the unsafe parts, of course. And then we have functional correctness and so on. So far, with this project, we are focusing on these parts. With the goal of extending up the pyramid in the future, and hopefully efforts on the hardware property side also eventually giving us something we can build on the hardware side. So we are currently working on verifying the memory safety and functional correctness of core parts of the code, in particular focusing on unsafe code. And that's why we are also using RefinedRust for this. The unsafe code in the implementation is one of the key risks. And this is fairly well supported by RefinedRust. Of course, the foundational angle is fairly interesting because we are verifying the core foundations of a trusted computing environment here. And if you verify the core foundations of such a system, this is I think worth the additional cost of doing foundational proofs. And then there's the hope that RefinedRust and its soundness proof can be extended in a relatively straightforward way to eventually link with an authoritative ISA specification and proving security properties. But this is future work at this point. Okay, that's it for my talk. If you want to use RefinedRust today, here's a link where you can find more resources. We have a tutorial that you can use to get familiar with the basics, but I'll admit that the documentation isn't great currently. We're working on that, and of course, I'm happy if you have suggestions. We're continuously adding more features, for instance, supports for traits and closures. But there are clear limitations currently. For instance, when it comes to unsized types, you can see a table here. If there's an X there, then we basically don't have support for that. if there's the yellow tilde there, then we have support for some cases of that, or maybe also many cases, but not good general support yet. That you can expect to work in all cases. And if there's a green check mark, then it should mostly work. But this is still an active research project. It's not totally stable, and it's still likely that you will occasionally encounter bugs. I'm happy to help in these cases, and if you want to use it, but I would say currently it's less stable than many other Rust verifiers. Okay, that's it from my side. If you have questions, please go ahead.
All right. Thanks, Leonard, for the talk. If you have questions, I guess you can use the raise hand emoji. Or alternatively, the first person can just speak up.
So could you go in, thanks first of all for the great talk. Could you go into the limitations currently regarding interior mutability and concurrency?
Right. For concurrency, our model is we are concurrency aware, so that we everything that you verify is concurrency safe, according to what you would expect, according to the Rust notion of concurrency. But we haven't verified any concurrent code actually. So we don't have, for instance, specifications for the useful parts of the standard library that you would want to use to verify concurrent code, because we just haven't done that. For interior mutability, we have support for non in the RustBelt sense non-atomic interior mutability. Vincent worked on that, and that should work. We have not added support for, in the RustBelt sense, atomic interior mutability that you'd use, for instance, to verify the concurrency primitives. Yeah.
Thanks.
So things like cell, for instance, should work. The concurrent versions not.
Another question, the aliasing restrictions.
What do you mean?
Are you sound with respect to Rust's aliasing restrictions, tree borrows, etc.?
I mean, we do not implement an aliasing model like tree borrows or stack borrows, because that is not an official part of semantics right now, and that would be a very sizable chunk of additional research, I think, to verify programs with respect to those aliasing models.
Thank you.
Okay, there's a question in the chat from Julian. I'm just going to read it out loud for the people watching the recording, which is that as part of the collaboration with IBM, are the engineers at IBM working directly with RefinedRust by either writing specifications or writing and verifying them? Or are they rather consultants for you to figure out the specifications and then you do the verification? So I guess the implied question is, how usable is RefinedRust for non-PhD students in verification, but like actual engineers?
That's a good question. I'm mostly doing the specifications and the verification. The IBM people are mostly not people, or like, except for one person, are not people who are familiar with much of formal verification, but rather are security engineers familiar with building trusted computing environments. So they have informal invariants and so on paper, and then I'm working on together with them to formalize that. As to the implied question, I would say probably if you have no formal verification experience, then it will be hard to use RefinedRust at this point. At some point, especially if you verify unsafe code, you will run and you will have to hack around in Rocq. If you don't have any formal verification experience, probably you will run into trouble. Right. I see a question by Safla. Have you found interesting
I think Ralph was first.
Sorry.
Yeah, sure. Thanks for the update, in particular about the IBM collaboration. I was wondering about one thing, not very close to your project, but in describing the context of the project, you said, as a user of the cloud, I shouldn't even have to trust IBM. And I don't see how this project can possibly achieve that, because I still have to trust IBM that they're actually running. Like, I ultimately have my data on their system. And there's pretty much absolutely nothing, as far as I can tell, that means that we can't trust them.
Right.
So I was wondering if you were, I mean, I know the marketing departments of these cloud companies like to make claims like that, but I as far as I can tell, they have zero technical basis. So I was wondering about that.
Right. Right. So this is, of course, providing these guarantees is out of scope of the formal verification part that we're working on right now. What you can do this technically is attestation, using remote attestation or local attestation, where you have some cryptographic seed in the hardware somewhere, and somewhere that part you will trust, of course, or you will have to trust, and then the security monitor cryptographically together with the hardware cryptographically makes sure that the virtual machine image that you're booting in the end, as well as the firmware image that you started from, is matches with what expectations you had. So I mean, there's in the end the root.
I still have my data unencrypted in their RAM, right? Like, unless I put everything into the enclave, which I don't typically do because they are super resource constrained.
The idea with this project is, or with this confidential computing architecture, is that indeed everything is in your enclave. Everything is in this confidential virtual machine that you need to trust.
Well, I thought these enclaves, like, what are they called? x86 something.
These are not enclaves. This is a different form of confidential computing, and I'm not an expert on the x86 stuff and so on, but don't think of this in terms of enclaves. This is implemented pretty differently.
Right, but then at the end the data is unencrypted in RAM. So not sure how I can do anything without trusting IBM. I just don't buy that claim. I think it's smokes and mirrors. But other than that, the technical work I think is really cool.
Yeah, for the RAM, I guess the idea is that you use RAM encryption and
yeah, but who encrypts the data? I mean, the code, the key is also in RAM, and like it's all on IBM's machines.
Okay, I think Ralph, we got your point.
Yeah. I mean, somewhere there's some root of trust in the hardware that you will have to trust, and there's I think I'm not a confidential computing expert who are to argue with that, but yeah.
Okay, I guess there was the question from Sasha also that you already started reading, which is whether you found any interesting bugs in the ACE code so far.
We have some. We found some minor things which I don't know if they would have been exploitable or not. Nothing serious, I think. The code, I think, is fairly well engineered and was written with like having pretty clear invariance from the start, and has relatively minimal unsafe Rust code. There are in total, I think, maybe 200 lines of unsafe Rust code or so in the code base, and yeah. But I think maybe we'll find some glaring things as we go on in the verification. Currently, we are focusing on the core parts of the system.
Cool. This raises an immediate follow-up question. How much code is there that you want to verify, you have verified, you still want to verify?
Right. In total, the parts that we want to verify are about, I think, 4,000 lines of code. So this is a pretty significant chunk. We have verified so far in the order of several hundreds of lines of code, 500, 600 lines of code. We are relatively early in the actually verifying phase because we spent a while actually stabilizing RefinedRust and adding support for features that you encounter in a real RefinedRust in a real Rust code base, like traits and iterators and fun stuff like that we didn't have in RefinedRust originally. Yeah, that's like about those dimensions.
All right, cool. Does anyone else have a question?
I do. I have
Ah.
another sort of UX related question. Has there been any part of RefinedRust or the RefinedRust like workflow that you've particularly enjoyed or taken advantage of? And maybe also sort of like symmetrically, has there been anything that you feel like has been a pain point in verifying code with RefinedRust?
That is a good question. Let me think. I mean, one thing that I enjoy is like that we have relatively good automation for passing ownership stuff around, also for unsafe, and that usually works as you would expect. Pain points in the workflow. I mean, sometimes you end up stating fairly obvious properties, especially when you state specifications for closures that do relatively simple things, and then you give a specification to the closure, you give a specifications to all the captures and so on, and there should be something which deduces this from the Rust code already. I think because kind of the Rust code in many cases is pretty functional. So like,
Yeah,
why am I specifying this again?
we actually added a feature specifically for that in Crusoe, where because especially for closures, right, your code is usually just like one line call function f with like 2 parameters or whatever.
Yeah.
Yeah.
Nice.
Okay. Yeah, this is interesting. This makes sense to me.
Yeah. Otherwise, of course, the main pain point I think is this is not really avoidable is wrestling with Rocq when you prove side conditions about pure facts, and that sometimes gets pretty painful.
Okay, I have a final question, which is predicated on my understanding of RustBelt. So at Ralph, if I say anything wrong, please catch me. But as far as I understand, in RustBelt, you like have Rust's type system, but then the language that the code is actually written in doesn't really look a lot like Rust. So I'm wondering, how much did you have to like redo the proofs in RustBelt to Lithium? Like, did you have to basically redo most of the type safety proof, or how much could be adopted?
Yeah, I mean, basically, like this is we had to redo a fair bit once because we have functional properties now, so refinements. The other thing is this year RustBelt, I think, doesn't really have a very satisfying way of handling places and how you handle it when you access stuff like this first component here, and that made it not obvious how we would mechanically translate the Mer code into the style of type system and approach that RustBelt does for places. So basically, place types were a significant chunk of the effort in order to make this translation very mechanical and make it look like surface level, basically make it look like Mer.
Ralph?
Maybe if I can have a final question. You mentioned annoying pure set conditions. So the separation logic and actual code part of the proof is fine. It's only the pure set conditions that are causing annoyance. You're not. I mean, I heard this before. It's interesting. I'm not entirely sure why that happens, but it then makes me wonder. Like, okay, so should we look into hooking an SMT server into Rocq just for the pure parts or anything like that, right? Like it's interesting that it seems to be the pure set conditions always and not the separation logic part.
Yeah, I mean, in my experience so far, the separation logic part mostly like works pretty well. The separation logic part fails occasionally, and then that is because some typing rules in the RefinedRust type system are incomplete or not working as intended yet. And that is usually like a one-off fix. You fix it once, and then you don't see that same kind of thing anymore. So that I think is converging to a place where you don't see these kinds of things anymore. It might also be the case that for the separation logic part, at least, like you sometimes if you manually specify ownership things, you have to be careful how you phrase them. And if you know how to phrase them in a way that the separation logic automation can handle them well, then you won't get any trouble. But if you come in as an unexperienced user, then you will probably run into more trouble with that ownership things. But that said, I think the pure facts are much more of a problem for handling things. And on Xavier's question, it's usually not dependent typing related stuff. It's really pure facts that, like for instance, about lists that are not very well automated generally. Or if you add new custom inductives, and then you need to reason about them, and then that you spend some time trying to figure out how to automate it well.
Same problems the SMT users also talk about.
Okay, yeah, that might be the case, but I think probably like to some extent the stuff, especially when it comes to integers, for instance, like probably SMT solvers would help. Would be very cool if we had a really good, well-working integration into Rocq, but then and then sometimes trade off between do you want foundation or do you trust the SMT solver a bit?
Yeah, I mean, for integers, yes, definitely. On the other hand, if you look at the tools which are like some of the recent SMT-based tools, like CN, they only send linear integer problems to the SMT, and then you can just use Lia and Rocq, right? So it's interesting to see that SMT side. Anyway, fun discussions to be had here. Thanks for the presentation.
Thanks.